All right, let's talk about something that is deeply, and I mean frustratingly familiar to so many of us, the sleepless night. We're going to break down the science of what's actually happening inside your brain when you just can't seem to switch off. Oh, you know this feeling, right? You are physically exhausted, you've been running around all day long. But the second your head hits that pillow, bam, your brain is suddenly wide awake. It's time to solve all the world's problems, or maybe just replay that one awkward thing you said in 2007. It's that classic tired but wired feeling. So here's the absolute key idea from all the latest neuroscience. Insomnia isn't about failing to get sleepy. It's the complete opposite. It's an active state of being too awake, a state of hyperarousal. It's like your brain has a master wake switch and it's gotten jammed in the on position. And today, we're going to figure out exactly why that happens. Okay, so here's our game plan. First, we're going to look at the sleep switch itself. Then we'll meet the two opposing teams of brain chemicals that are constantly fighting for control. We'll call them the wake team and the sleep team. After that, we'll see what's going on when that switch gets stuck, look at two main ways to fix it, and wrap up with this really tricky problem of getting the timing just right. So first things first, falling asleep isn't like your computer just powering down. It's not passive at all. It's actually an active process. A much better way to think about it is like a biological battle going on between two really powerful opposing systems in your head, and they're both fighting for control of one single critical switch that decides if you're awake or asleep. And hey, if this whole battle in your brain thing sounds a little too familiar, well, you are not alone, not by a long shot. Some sources show that up to half of all adults deal with insomnia from time to time. So yeah, you're in very, very good company. To really understand how this switch works, we've got to meet the two sides. So let's start with the wake team. This is basically a whole crew of neurochemicals, and their entire job is to keep you awake, to promote and stabilize that feeling of being alert and focused all day. Now, every team needs a captain, right? For the wake team, that captain is a neurochemical called Orexin. And Orexin is interesting. It doesn't just make you feel awake on its own. It's more like a conductor of an orchestra. Its job is to coordinate all the other arousal chemicals to make sure that on signal is strong and stable all day long. And one of the star players on that team is histamine. You probably know that name. Ever wonder why allergy medicines, antihistamines, make you so drowsy? Well, it's because they work by blocking this exact chemical, a really powerful arousal signal in your brain. When histamine is doing its thing, you are alert. So here's the whole lineup. You've got Orexin conducting the show, and it activates all these other players. Histamine, norepinephrine, dopamine, you name it. Together, they create this one powerful, unified signal that keeps your brain's master switch flipped firmly to on. But obviously, the wake team can't be in charge forever. So, enter the sleep team. And here's the thing. Their job isn't to just wait around for the wake team to get tired. No, their mission is to launch a direct counterattack, to actively shut down the wake team so they can flip that switch over to off. The star player for the sleep team is a chemical called GABA. You can just think of GABA as the brain's main brake pedal. It is the primary off signal. When it gets released from a special spot in the brain, it goes to work and directly quiets down all those arousal circuits we just talked about, getting the brain ready for sleep. So what tells the sleep team it's time to get to work? Well, it's two main things. First, there's something called sleep pressure. All day long, a chemical called adenosine builds up in your brain, and the more you have, the sleepier you feel. And second, you've got your internal body clock, your circadian rhythm. As it gets dark out, that clock starts telling your brain, all right, time to start winding down. Okay, so we've met our two teams. In a healthy brain, as that sleep pressure goes up and the body clock winds down, the sleep team just smoothly takes over from the wake team. But in a brain with insomnia, that handover fails. The switch gets stuck. And this quote from the research just says it perfectly. This is the new way of thinking about it. The problem isn't that your sleep team is weak or that it's not showing up for work. The real problem is that your wake team is overactive. It's refusing to power down. It's fighting back when it's supposed to be quiet. It really is just a simple imbalance. In a healthy brain, the wake team chills out at night and the sleep team takes over. No problem. But in an insomniac brain, that wake team stays totally revved up. It creates a state of hyperarousal that the sleep team just can't push through. You are tired, but your brain is still switched on. So, if the problem is just a stuck switch, then the ways to fix it become pretty logical, right? We can basically approach this from two different angles, and these line up perfectly with two major strategies in sleep medicine. Okay, so here are our two strategies. Option 1, you can power up the sleep team. You make their off signal, that GABA stuff, way stronger. Or option 2, you can try to quiet down the wake team directly. You block their key players like Orexin and Histamine so they can't shout so loud. And this is exactly how most common sleep medications work. You have the classic drugs like benzodiazepines and Z-drugs, which are all about boosting the sleep team's GABA signal. Then, you have newer medications, and even just regular old antihistamines, which work by blocking the wake team's signals. Two completely different ways to get to the same goal. But there is one final, crucial piece to this whole puzzle. It turns out it's not just how a drug works that matters, it's how long it works for. This is the just right problem, and it's all about trying to match a drug's activity to a perfect night of sleep. And you've probably wondered about this. It's like the Goldilocks dilemma of sleep aids, right? How is it that one pill can leave you feeling like a zombie the next morning, while another one wears off and you're wide awake again at 4 in the morning? Well, the first problem is the too cold scenario. This is when a drug works, but its effect is just too short. It's great at helping you fall asleep, but then the drug level in your system drops below the sleep threshold in the middle of the night. The result? You wake up way too early and you can't get back to sleep. And the opposite problem is when the effect is too hot. It lasts too long. Now, the drug keeps you asleep all night, which sounds great, but the issue is its level is still above that sleep threshold when your alarm clock goes off, and that is what causes that awful, groggy next-day hangover feeling. So the goal, the just right solution, is to find a drug profile that can thread the needle, something that gets you to sleep, keeps your brain above that sleep threshold for a full 7 or 8 hours, and then clears out of your system right before you need to wake up so you feel refreshed and alert. So there we have it. We've gone from this simple, really frustrating problem to seeing this incredible, complex dance between neurochemical teams fighting over a biological switch. And just understanding that it's really about an overactive wake team, not a weak sleep team, has completely revolutionized how we treat this. It really makes you wonder, if we can target this brain switch with this much precision now, what does the future hold? Are we getting close to being able to actually design perfect sleep? Definitely something to dream on.